So the last module we're going to cover is Module 11D for this chapter, which is molecular orbital theory. So you need to think about your electron configurations. So back from the previous chapter we covered electron configurations. You need to pull that back. You're going to be looking at electron configurations for homonuclear diatomic molecules or ions. So your diatomics, remember those? Hopefully. Determine the magnetic character of any homonuclear diatomic molecular ion. So is it paramagnetic or diamagnetic? We pull those terms back. We've learned it before. We're going to pull them back. You're going to determine bond order, meaning does it have a single bond, double bond, or triple bond? You're going to identify and be able to use the concept of bonding molecular orbitals and anti-bonding molecular orbitals. Bonding are just lower in energy. Anti-bonding are higher in energy. Use MO theory to explain the paramagnetism of dioxygen. Why do we see that oxygen is paramagnetic? Write your molecular orbital diagrams for given diatomic species, comparing bond orders and relative stabilities, bond energies and bond lengths, and describe the phenomenon of delocalized electrons and how this impacts the molecule's bond lengths. This stuff comes back heavy in organic, so if you're going to take organic, you really need to know it. Even if you're not taking organic, you need to understand how this is pulled together. So molecular orbital theory. Remember, so we just covered valence bond theory. In valence bond theory, an electron pair bonds using overlap of atomic orbitals from the two atoms. So in molecular orbital theory, all electrons in a molecule fill up one set of molecular orbitals that are made up of what we call a linear combination of your atomic orbitals from two or more atoms. We'll get more into this, but what I mean by that is when we talked about atomic orbitals, it was like for carbon, I said 2s and 2p. That's an atomic orbital. If I had another carbon, if these were the same energy level, because that's what I'm trying to write, would these combine? How would these combine? These are two different molecules here. How would they combine to form one molecular orbital? Localized is when the combination of atomic orbitals comes from two atoms. Delocalized is when the combination of atomic orbitals comes from three or more atoms. So you can think of molecular orbitals in this fashion. They are formed from a linear combination of atomic orbitals, and I will get into that. I promise I will show you what that means so you'll be able to see it visually. There are two important types of molecular orbitals, though. We have bonding molecular orbitals and anti-bonding molecular orbitals. Bonding are just lower in energy, while anti-bonding are higher in energy. So you're going to determine the molecular orbital electron configuration. To do this, it's analogous to determining your atomic orbital electron configuration. Molecular orbitals are weighted linear sums of the valence atomic orbitals of all the atoms in a molecule, and many of the molecular orbitals are delocalized over the entire molecule. That probably means nothing to you right now, and that's okay, because we're going to see how it's applied. But basically, we take those atomic orbitals, we take those, where we put the electrons in from your electron configuration, we mix it together and see how it comes together for a molecule itself. So in molecular orbital theory, electrons are under the influence of all nuclei in the molecule. Quantum mechanics tells us electrons in your bonding molecular orbitals are stabilizing, meaning they're lower energy than the atomic orbitals. Electrons in anti-bonding molecular orbitals are destabilizing, they're higher in energy than your atomic orbitals. The electron density is located outside of your internuclear axis. Electrons in an anti-bonding orbital cancel the stability that's gained by the electrons in the bonding orbitals. So why are they created? Well, they need to be by the theory. We have them. We can't have everything, not everything's going to be lower. If we form a bonding orbital, we're also going to form an anti-bonding. That doesn't mean there's electrons in both spots. It means that there's orbitals. Bond order in molecular orbital theory. The bond order is the difference between the number of electrons in the bonding and anti-bonding orbitals. We only need to consider valence electrons. This value may be a fraction, And the higher the bond order, the shorter and stronger the bonds. If bond order is 0, the bond is unstable compared to the individual atoms and no bond will form. If it's 1, it's a single bond. 2 is a double bond. 3 is a triple bond. And this is the strongest. A substance will be paramagnetic if the molecular orbital diagram has unpaired electrons. Remember paramagnetic? Unpaired electrons, it reacts in a magnetic field. If all electrons are paired, it is diamagnetic. It is not magnetic, meaning it does not react in a magnetic field. To find your bond order, you take the number of bonding electrons you have, subtract the number of antibonding electrons you have, and divide by 2. Some terms you just need to know. Homo Lumo, your Homo Lumo gap. Homo is your highest occupied molecular orbital. What is the highest orbital I have that electrons actually reside in? Lumo, your lowest unoccupied molecular orbital. It's your lowest orbital, lowest meaning in energy, without electrons. And your Homo Lumo gap is the energy difference between Homo and Lumo. This Homo Lumo gap comes into play in solid state chemistry. This is why I see things like, why metals conduct electricity really well and nonmetals don't. It's based on their Homo Lumo gap. Nonmetals have a very large Homo Lumo gap, while metals, their Homo Lumo can actually overlap almost. And bond order, a positive bond order implies the molecule is stable. So bond order, again, number of electrons in your bonding molecular orbitals minus number of electrons in your antibonding molecular orbitals divided by 2. If it's paired magnetic, the atoms or ions, that atom or ion contains unpaired electrons. Therefore, it's attracted by an external magnetic field, or it is magnetic, is another way to think about it. Diamagnetic, atom or ion that contains only paired electrons. Therefore, it's repelled by an external magnetic field. It's not magnetic. And a node is the point in where the wave function psi, and therefore probability psi squared of the radial distribution function is 0. A node, it's a fancy way of saying that, like on a pi orbital, or a p orbital, your node, no electron resides. That should say node. It's void of electron density. So let's go ahead and work some examples here. So first we're going to talk about H2. Sorry, one second. I'm trying to make sure I wrote... Okay, I have one more thing written down that I don't... Sorry, I was looking for this piece of information right here. Like this, here and here. It's, I think, what I was looking for. Okay, so for hydrogen, there are 2 atomic orbitals from one hydrogen, for 1s. So hydrogen has 1s, 1 electrons. We're going to recreate what's over here, but we've got your 1s with its 1 electron. We have your second hydrogen, also with its 1s, 1 electron. So 2 atomic orbitals, 1s from one hydrogen, 1s from second hydrogen. Therefore, there are 2 molecular orbitals. 2 orbitals in, 2 orbitals out. We call one your bonding orbital and one your antibonding orbital. And because we know hydrogen is going to form sigma bonds, it is called a sigma orbital, bonding orbital. So the first one that forms is bonding. It's a sigma 1s, and this is a bonding orbital. We're also going to form a higher energy, sigma star 1s. Sigma star means antibonding. Higher in energy. In this molecular orbital diagram, once the 2 electrons are entered, only the bonding molecular orbital is filled. So just like before, each orbital can hold 2 electrons. The bond order is 1. I take the number, so this is bonding, this is antibonding. I take the number of bonding electrons, which is 2, subtract the number of antibonding electrons, and divide by 2, and I get 1. That tells me that hydrogen has a single bond between the 2 hydrogen atoms in H2. Bond order is 1, it's greater than 0, therefore it is stable. It's the same, so what we're seeing here, it's what we just basically redrew what we have here. But sigma star tells me antibonding. The star itself tells me antibonding. Sigma bonding. And basically we took your 2 1s electrons, the orbitals overlapped, we have our bonding and our antibonding. You need to be able to draw these. You need to be able to understand this. The antibonding has a node between it. They are higher in energy. Doesn't mean we don't fill that up. Things can go there, yes. Let's look at H2. Or He2. Sorry, we just did H2. Helium, He2. If I looked at He2, I know helium has 1s2. So each helium has 2 electrons. 2 orbitals in, 2 orbitals out. I get my sigma and my sigma star. I have 4 electrons total. Each one can hold 2. 1, 2, 3, 4. Both my bonding and my antibonding are filled up. Find out my bond order. I've got 2 bonding electrons and 2 antibonding electrons. That gives me 0 divided by 2 gives me 0. Bond order is 0. Molecule is not stable. Makes sense to us, right? Helium doesn't want to bond. It's got its perfect octet for itself. But molecular orbital theory is backing up that it's not bonding because our bond order is 0. The compound is a bond order of 0. Because we've got an equal number of bonding and antibonding orbitals, therefore it's not stable to form the bond. What about your second row diatomic molecules? Nitrogen, oxygen, fluorine, etc. We're going to start drawing a lot of these out, and I'll draw more of them out in a sec. But atomic orbitals are combinations. Some your s orbitals and your p orbitals. So you can have them combine and form these different structures. The 2 p's, side-to-side overlap here, we see bonding and antibonding. So you've got your nodes here, okay? So even on p orbitals, you've got your node here. You're still going to have your node. This is still called bonding. We've just got 2 areas of electron density. This is antibonding. You've got now a node here that's been created from the antibonding and the original node. The p's here overlapping. This becomes one giant area. We still got a node here and a node here. In antibonding, we get the node in the middle that's created as well, in addition to what we already had. Another thing to note here is that the molecular orbital energy level diagrams will change slightly depending on which element we're looking at. If you are below nitrogen on the table, we're going to do a bunch of examples like this, but below nitrogen, we fill our 2p's before we fill our sigma. Once we hit oxygen, we fill our sigma before we fill our p's. These are from your 2p orbitals, by the way. But oxygen forward, sigma first, then pi. Up to nitrogen, pi first, then sigma. You have to know this. You have to know that this is happening. I will draw these out in a sec. Just give me a sec to get through these. But you have to remember that if you've got nitrogen below, you're doing pi first, then sigma. If you're doing oxygen, you're doing sigma first, then pi. How do we know this? Experiment. We know this because experimentally we can tell what's happening. So let's go ahead and work some examples. I know I skipped a few in your notes, and I'm going to go back and work those as well. Let's see. Okay. Yeah, I'm going to go ahead and just put a piece of paper in here so that I can work these out for you that are in your notes, okay? So if I've skipped it from your notes, we are going back to that, I promise. So first example here, we've already done hydrogen. We've done He2. Let's do He+. He2+. Is this stable? We know that helium normally has 2 electrons. But in this case, I've got 1s, and I've got another 1s, but I'm missing 1 electron because I've got He2+. I'm going to form a bonding orbital and an anti-bonding orbital. S orbitals only form sigma. So I've got sigma and sigma star. This is sigma from a 1s, sigma star from 1s. Sigma star means anti-bonding. Just sigma means bonding. I'm going to combine my electrons, 1, 2, and 3. I'm going to determine my bond order. 2 bonding electrons minus 1 non-bonding electron divided by 2 gives me a bond order of 1/2. What that means is that it's greater than 0. It could actually exist. It's a half a bond between them. So bonding MOs, molecular orbitals, are designated sigma and pi molecular orbitals. Antibonding molecular orbitals are designated, with sigma star and pi star molecular orbitals. The star tells me anti. And we do pronounce this sigma star and pi star. Two s orbitals will combine to form 1 sigma and 1 sigma star. two head-to-head p orbitals will combine to form a sigma. They don't have to be one here. They could be, I meant just one in general, not like the numbered one, not like 1s. But they form sigma and sigma star. Two parallel, meaning side to side, p orbitals will combine to form pi and pi star. So for sigma, sigma star, we saw sigma, sigma star. For pi, we have pi and pi star. Two parallel means 4 out. 2 in means 4 out, or means 2 s orbitals means 2 out. Two parallel means 4 in, 4 out. Because I got 2 from each side coming in. The general order of filling when you're making these, what you're going to find is you're generally filling sigma 1s, sigma 1s star, sigma 2s, sigma 2s star, just like we fill our atomic orbitals. Now we've got to pay attention to if we have nitrogen or oxygen first, but you've got either your pi or sigma from your 2p's, and then you've got the opposite, pi or sigma from your 2p. But these are bonding, so be careful. Which one's first? Let me specify here. So we're going to fill your pi 2p first if you have nitrogen or below. Sigma if you have oxygen or above. Nitrogen or below, you're then going to fill your pi star and sigma star. Oxygen and above, you're going to fill your sigma star. Oh, sorry. Thinking about that backwards. You're still going to fill pi star, sigma star. It's only these that get switched. Well, again, I'll show you that example in just a sec. So, pause the video if you need to write this down. I need to go back up and figure out where I was last writing. Okay. So this is what they're going to look like. Now let's work some examples. I want to work carbon, boron, fluorine. I'm also going to work oxygen for you. So I'm going to go back up to this sheet here and work oxygen for you. So if I look at oxygen, oxygen has electron configuration 1s2, 2s2, 2p4. Sorry to keep moving the screwdriver. It's just going to take a lot of space. And I can't write a straight line to save my life. Okay. So I've got my 1s with my 2 electrons. I'm going to fill those in first. It's going to form a bonding and an anti-bonding. Sigma 1s, sigma star 1s. Fill in my electrons, 1, 2, 3, and 4. Probably going to need a lot more space because I don't know how to write these small. So I'm going to move that down. Next, I'm going to fill my 2s. My bonding and my antibonding. One, 2, 3, 4. Sigma 2s. Sigma star 2s. Now I'm onto my 2p's. And remember, for oxygen, this is where it switches, what I was talking about before. So what I'm going to fill first for oxygen is I'm going to fill my sigma bonding. Sigma from my 2p, sigmas always have one orbital. Then I also have my pi bonding 2p. Above, I have my pi star, which means pi antibonding. And my sigma star. And then fill in your electrons. So I've got for oxygen 1, 2, 3, 4, 1, 2, 3, 4. So that's 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. This whole thing is the complete molecular orbital diagram for oxygen. If I do bond order, if you have completely filled like this and this, the bond order comes out to 0, so I just ignore it. Do the ones that are not, that your last one that's not completely filled. I've got 2, 4, 6 electrons in my bonding. Got 2 electrons in my antibonding. Divided by 2 gives me a bond order of 2. When I look at oxygen, if I was to draw out the Lewis structure, I would find that oxygen is double bonded to itself. So, yep, bond order of 2 makes sense. I also can determine if it's paramagnetic, though. Remember, paramagnetic means unpaired electrons. It's paramagnetic, all right. I've got my 2 unpaired electrons right here. So oxygen will be magnetic. It'll be affected by a magnetic field. We also want to do carbon, boron, and fluorine, the molecular orbital diagram, electric configuration, the bond order, and the magnetic character. I'm going to draw these ones on the diagram above, though, because it's easier than drawing them out by hand. You do have to draw them. You have to be able to be responsible to draw these. And you have to know which appropriate one to use. But for simplicity, and because I don't want to have to, because my iPad's now at 6% and I want to finish this video at some point, I'm going to draw them on here. So first one we're going to do is, sorry, I don't have my glass on, but it's carbon. If I look at carbon, 2s2, 2p2. So 1, 2, my other carbon, so I've got carbon on each side, one carbon, right? 2s2, 2p2, 2s2, p2, 2p2. Fill in your electrons. 1, 2, 3, 4. 1, 2, 3, 4. Look at your bond order. So this is my molecular orbital diagram. Now I want to find my bond order. Number of bonding electrons. You can do all of them if you want to. If you feel more comfortable, Count up all of your bonding electrons. You're going to get the same answer, and I'll show you. You got 4. Count up your non-bonding electrons. You've got 2. Divided by 2, that's going to give you 1. You could also do it by just looking at the highest level. We would say bond order, 2 bonding orbital electrons, 0 non-bonding, divided by 2 also gives me 1. So this has a bond order of 1, which tells me it is a single bond. And because I have, excuse me, no unpaired electrons, it is diamagnetic. But note for carbon, we filled your 2p's before, your 2p pi bond orbitals before your sigma. For oxygen, I filled sigma before I filled your pi's. So you've got to pay attention to which one you're filling here. Boron, we see something similar. Boron has an electron configuration 2s2 2p1. So 1, 2, 3, 1, 2, and 3. 1, 2, 3, 4, 1, and 2. Bond order. Again, you can look at all of your bonding or electrons if that's what makes you feel comfortable. We've got 4 minus our antibonding. Minus 2 divided by 2 is 1. You could also just look at, just because this is completely full, it cancels itself out. You could look at just the top one and say 2 minus 0 divided by 2. Either way, single bond. And then, is it paramagnetic or diamagnetic? It is paramagnetic. It has unpaired electrons, which means it will be attracted in a magnetic field. The last one I want to do for you guys is fluorine. Note that fluorine is over here. I'm going to fill my sigma before my 2p's. So fluorine, 2s2, 2p5. 1, 2. 1, 2, 3, 4, 5. 1, 2. 1, 2, 3, 4. 4 and 5. 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Bond order here. Got 2, 4, 6 bonding electrons. 4 antibonding electrons. Gives me a single bond. And when I form F2, it is in fact a single bond. And this is diamagnetic. I have no unpaired electrons, so not attracted in a magnetic field. Again, I did it on here because, well, my iPad's about to die and I gotta go find the charge. I gotta go to a different place to find the charger. But you guys do have to draw these out. You can draw these out, I promise. I drew out oxygen for you guys. Practice these. You will need to be able to draw these. You will need to be able to remember that nitrogen and before, we fill pi before sigma. For oxygen and after, we fill sigma before pi. So you have to know that. You have to keep that straight. You have to be able to draw stuff like this. Stuff like this. You have to be able to tell me my MO electron configuration. That's these diagrams. Bond order, magnetic character. Okay? So, to finish this out, by combining atomic orbitals from 3 or more atoms, it is possible to generate molecular orbitals that are called delocalized, meaning the electron density is shared over an area of 3 or more atoms. This is how resonance works. We talked about resonance and how the electron, some resonance structures contribute more or less than other resonance structures. This is how they share that. By combining atomic orbitals from 3 or more atoms, the electron density becomes delocalized. Resonance in species like a formate ion, HCO2-, as shown here, benzene, which I'll show as well, can be explained with a single molecular orbital description containing delocalized p orbitals, or p bonds. So the electron density, instead of just one bond, resonance is explained because we're sharing that electron density over an entire area. This is how your true resonance hybrid exists. This is benzene. Benzene is C6H6, and benzene has alternating single and double bonds around its molecule. So it's got pi bonds in here. What happens is the electron density is delocalized around the entire area, above and below. It's a planar molecule, but it's delocalized above and below the molecule. So this is just showing you your sigma bond portion. This is showing you your pi bond portion. But it's delocalized, meaning it's all shared equally around that whole area, hence a resonance structure. Yes, some resonance structures contribute more than others, but if they all contribute equally, it's an equal distribution here. If they don't contribute equally, well, it's still delocalized, and we can use molecular orbital theory to explain that delocalization. It's just some structures contribute a little bit more. And that's the end of this section. Go ahead and please review this, and please look at the additional practice for some more help.